A toroid, on the other hand, is nothing but a solenoid which is bent in the form of a ring. So you can see in this picture here, this is a toroid which has nothing inside it. So that means there's just air inside it. In other words, we say it is an air-cored solenoid. But here there is some substance inside of the solenoid. Inside of the toroid. Okay, so let us find the expression of the magnetic field inside of the toroid. Let's say we have a toroid in this figure here. So the current I is entering the toroid in that manner, and it is leaving the toroid from this point. So in order to find the magnetic field using the Ampere's circuital law, we have to take a closed loop. We consider a closed loop, and let us consider a closed loop of radius r, a circular closed loop of radius r. Okay, so let n here, small n, be the number of turns per unit length of the toroid. I is the current passing through the toroid, and B the magnetic field inside of the toroid. All right. Now in this circular loop, we are considering a small length of the loop, dl. And this small length is at a distance r from the center of the loop, which is actually the radius of the loop. Got it? So by Ampere's circuital law, the magnetic field, the line integral of the magnetic field B dot dl, this is equal to mu naught times the current passing through, not through the entire toroid, it is the current passing through the loop. So this will be mu naught times the current passing through the loop. Okay, so that will be mu naught, and the current passing through the loop will be what? It will be the number of turns, because the current is not going only once. It is going entering, leaving, entering, entering, entering the loops like this. How many times is it entering the loop? It is entering n times. Okay, and from this point it is entering along the entire stretch of this loop. In other words, it is entering along the entire circumference of the loop. So therefore this will be times the circumference into I. Okay, so if you write here just I, then that would be wrong, because I is the current passing through only one turn of the loop. But the current, it is very clear here that it is not going only in one single turn of the loop. It is going through many turns of the loop, yes or no? So therefore we have to multiply n, and since the current is like going from this point, it is going round until it reaches the same point, and that path is equal to the circumference. We have to multiply with the circumference of the dotted circle here. Okay, and what is the value of this integration on the left hand side? Let us apply the dot product here. You have b dl cos 0 degree, and by now you know why this is 0 degree, because dl and b are along the same line, and we know that cos 0 degree is 1. So you have just b dl is equal to mu naught n 2 pi r I. Okay, let us take a new page. So this shows, this means that the magnetic field can come out, right? So you have mu naught n I 2 pi r. So what is the value of this integration? What is the value of this integration here? So this integration actually is nothing but you're taking a small length dl, and you're integrating over the entire circumference. So this will be equal to 2 pi r. Yes or no, this integration? So that comes out to be 2 pi r. So mu naught n I 2 pi r. This 2 pi r and 2 pi r will cancel, so you get B is equal to mu naught Ni, and this is nothing but the same as the expression for the magnetic field due to a solenoid, and that is expected actually. Why? Because the solenoid and the toroid are nothing but the same thing. The only difference is in the shape. Okay, so the strength of the magnetic field also will come out to be the same, right? So if the toroid has a core of permeability mu r, then B is equal to mu r mu naught Ni. Okay, and if you look at these two expressions, does the magnetic field depend on the radius of the toroid? Does it depend on the radius of the toroid? Yes, does it depend on the radius of the toroid here? You don't see any expression, any r out here in this expression, yes or no? So that means it is independent. It is independent of the radius of the toroid. That means the magnetic field at this point is the same as at that point, is the same as at that point, at the center, even at the edge, the magnetic field will always be the same, uniform. Is this clear? So this is the magnetic field due to a toroid.